What is up, everybody? Mr. Murray here. Some more solving of trig equations. And again, we're answering in radians and degrees from 0 to 2 pi, or 0 to 360 degrees, the equivalent. And as always, I'm going to imagine this scenario as if this is on a quiz or on a test. And so maybe you have the unit circle memorized, maybe you use triangles, maybe you use the chart, maybe you just know them all. I'm going to draw a little quick chart as reference. This is what I recommend if you have difficulty keeping those values straight. Sine, cosine, tangent, and like I usually say, don't just look at a pre-drawn one in your notes. Practice drawing it or doing whatever you would do on a quiz, because then it's just second nature to you when you need it randomly every so often, like will happen in calculus all the time. Okay, so sine, cosine, tangent, that's how we set this up if you want to do it this way. And then the angles at the top are in ascending order, so 30, 45, 60, smallest to biggest, just like if you were going on the unit circle in that counterclockwise order. And in radians, that's pi over 6, pi over 4, pi over 3. What are those values? Sine and cosine for all three are over 2 over 2 over 2, root 1, root 2, root 3 in order, right? And then the cosine is just backwards, root 1, root 2, root 3. Tangent is just sine divided by cosine, so 1/2 divided by root 3 over 2. These all have denominators of 2, so they cancel. Just focus on the numerators. 1 divided by root 3 is root 3 over 3 when you rationalize. For 45, root 2 divided by root 2 is 1. And for pi over 3, root 3 divided by 1 is root 3. Okay. That, coupled with your knowledge of quadrants, will usually get you where you want to be. We also have our quadrantal angles we may have to incorporate, but these are for the three basic reference angles. Okay, so now let's actually take a look at number 1 here. So number 1, I see that I have sine squared and sine in the same problem. So that's, two different trig functions. They're not like terms. So just like if I were solving an equation with x squared and x, what would I likely do? Probably bring everything over to one side and try to factor it. So that's what I'm going to do here. I'm going to bring everything over to one side. It doesn't matter whether you like to bring it to the left or to the right. So I'm going to add sine squared. I'm going to subtract sine of x. I'm going to subtract 1. Right about now I'm thinking, hey, it would have been easier to move that left thing to the right side. But hey, like, do things difficult. That's how math teachers operate, right? So on the left, when we compile everything, I'll have 2 sine squared minus sine of x minus 1 is equal to 0. And there was a reason I did like to do it, because I like to keep my quadratic term having a positive lead coefficient. If I had moved everything to the left, I would have had negative 2 sine squared, but not a big deal in that case. I would have just divided everything by negative 1. But now I'm trying to solve this, and what I have is a trinomial equal to 0. So if you take a look at this, there is no greatest common factor I can factor out. But I really would just factor this, this is the first one I'm doing on this video. So I would really just imagine that I was, say, this was 2a squared minus a minus 1 equals 0. Only instead of a, it's sine of x is what a is standing in place of. So how would you factor that trinomial? You might do a little AC method to help you do it. You might really be able to say, this is a pretty easy one to kind of just mentally figure out the pattern, right? Because in order to be 2a squared, one of these lead terms in the binomial has to be 2a and the other one has to be a. And then to multiply to negative 1, these two numbers here, one of them has to be positive 1 and one of them has to be negative 1. You just got to worry about the signs, which one is which. And that has to do with this, right? You think about if you FOIL, it should add up to negative 1 in the middle. So, I mean, there's a, throw a negative there and a positive there, and then just mentally do a little check. Your outers would be positive 2a and your inners would be negative a. So 2a minus a would give you positive a. and we want it to be negative a. So that just means I have the signs reversed. So I'll change this one to negative, this one to positive, right? And now that should be good. Negative 2a plus a will add up to negative a. So there's your factoring combination without having to do the big AC method, but you're welcome to do that. But now that was sort of standing in place for 2, and a was standing in place of sine of x. So that's 2 sine of x plus 1, and in the second binomial, that would be just sine of x minus 1. You can always FOIL it out to check if you don't trust the factoring. Make sure you're good. But we have factored it now, and like always, now we just set each factor equal to 0 and solve. So setting 2 sine of x plus 1 equals 0 means I subtract 1 and then divide by 2. And so I will have negative 1 divided by 2, or where does sine of x equal negative 1/2? For the second quantity, sine of x minus 1 equals 0, you're solving when does sine of x equal positive 1. So you got two little mini basic equations to solve in order to solve this overall, big equation. Okay, so first thing, where does sine equal 1/2? Think about the reference angle and the quadrants that would need to be in. Sine is 1/2 at a reference angle of 30 degrees, or pi over 6. But where is sine negative? Where is sine negative? Right, this is a smart trig class. All students take calculus, whatever you like, whatever mnemonic helps you remember the quadrants, which tell you where things are positive. So sine is positive in quadrant 1 and 2. We want to know where is sine negative. Quadrant 3 and quadrant 4 is where sine is negative. And the reference angle is pi over 6, as we said. So that would be in quadrant 3, 7 pi over 6, right? 1 bigger than the denominator. And in quadrant 4, that would be 11 pi over 6. Double the denominator minus 1. Or in degrees, the reference angle is 30 degrees. So in quadrant 3, 180 plus 30, 210. And in quadrant 4, 360 minus 30, 330. Okay. And now to solve this equation, where does sine of x equal positive 1? Well, that's not something, sine is not positive 1 for any of the three basic benchmark reference angles. So that should be jumping out to you as, hey, that's a quadrantal situation, and sine is the y coordinate, right? So where is the y coordinate positive 1 on this unit circle? Only one place. Right, that's this right here. The coordinates at this point are 0, 1. That's the only place where the y coordinate is positive 1. Right here is 0, negative 1. And so what angle is that? That is 90 degrees, or pi over 2 in radians. So pi over 2, or in degrees, 90 degrees. And so those are our three solutions in radians and degrees. But we had a little trinomial. That's really what this was more focused on, was factoring a trinomial, just like you would with Algebra 1, but now just going a little further with it, with trig. So just putting a lot of ideas together from previous years of math, coupled with what the new stuff we're doing. So let's just see a couple other examples and see how you feel about it. I'm going to bring that chart back here. There we go. Kind of tuck it off to the side. Now look at this nice trinomial. Sine squared plus 2 cosine x plus 2 is equal to 0. It's already equal to 0, except, hopefully this is catching your eye as something that's a little off. This is sine squared, and this is cosine. That's like having, x squared plus 2y plus 2 equals 0. That's like trying to factor that. Those are two different variables, two different functions there. I can't factor it as is. So what we need to do, and maybe your ideas are already popping, is I'm going to use a Pythagorean identity, right? And Pythagorean identities, you look to use them when you have a squared function. Sine squared, cosine squared, tangent squared, secant squared, any of them, there's a Pythagorean identity for it. And I have to use it here because I've got two different functions, sine squared and cosine. Whereas in the previous problem, just to recap, it was sine squared and sine. You know, it was the same trig function of sine of x. So, if you need a little refresher on those Pythagorean identities, the one that uses sine squared is sine squared plus cosine squared is equal to 1. So I'm going to take out sine squared. What is sine squared equal to? 1 minus cosine squared. So I'm going to take out that sine squared, like I said, and replace it with 1 minus cosine squared. And then everything else I'm leaving the same. So you see what I've done by swapping that out. Now it's all cosines. Cosine squared and cosine to the first in the middle there. So that's something I can deal with. Now I'm going to have to clean this up a little bit, combine your like terms and do some algebra, but at least now I've got cosines and cosines only in this problem. Okay, so combine our like terms. This positive 1 with that positive 2 is going to give you positive 3. So we're going to have negative cosine squared plus 2 cosine of x plus 3 is equal to 0. And I'm going to try to factor this now, but when our lead term has a negative coefficient, that's usually where I'll factor out a negative 1, or just divide everything by negative 1, or multiply everything by negative 1, however you want to think about it. It's all the same algebraically to get the job done. So I'm going to multiply everything by negative 1, basically just switching the sign. So now it's positive cosine squared minus 2 cosine of x minus 3 equals 0. And now we're ready to rock here. Factoring this, again, if it helps you to rewrite this as, hey, this is like a squared or x squared minus 2a minus 3 equals 0. If it helps you to do that, you know, go ahead. A lot of people will skip this step once they get comfortable. But hey, why not show it on the video? A squared. Now this one has a coefficient of 1 leading it off. So this should really be an easy one to factor. Right? It's just that classic pattern of a, and what multiplies the negative 3 on the end but adds up to negative 2. And you can put them in either place. So that would be negative 3 and positive 1, right? Because they're both a, you could put them in either place, and those binomials are good. And so what binomials are we really dealing with? I'm just going to swap that a back out. A was standing in place of cosine. So that's cosine of x minus 3 and cosine of x plus 1. Okay. So like I said, when you're comfortable with these, you'll probably go right to there, from there to there, and not have to do the rewriting. But if that helps you to see it, it does help some people. So hey, why not take an extra step or two? And now let's solve. Set each factor equal to 0. So when I set this factor equal to 0, I'll really be trying to solve where does cosine equal 3. When I set the second quantity equal to 0, I'll be solving where does cosine equal negative 1, right? And hopefully, you know, you're already popping. These numbers should be jumping out of you. Cosine being 3. Cosine being 3. That's certainly not one of the 3 benchmark reference angles. And if you think about it, is cosine ever 3? On the unit circle, the biggest the coordinate can ever be, and cosine would be the x-coordinate, the biggest the coordinate ever is 1. And the smallest it ever is negative 1. It's always an x value between 1 and negative 1 on this. So being equal to 3 for cosine doesn't have a solution. So hey, no problem. It just doesn't yield any solutions. Also, another way to think about it, which is a nice way to tie back to our graphing unit, is think about your cosine graph, which looked like this, right? What was the basic amplitude on cosine of x? 1. So there's that visual of, hey, the graph never went higher than positive 1 or lower than negative 1. So it never got up to 3. No solution there. But cosine being negative 1, that certainly does have a solution on this graph or on the unit circle. but only one solution. Where is that x coordinate equal to -1? Right here at 180 degrees, or pi radians. So there is my answer in radians and degrees, and only one for this problem, pi, aka 180 degrees. But the big thing here was not only a trinomial trying to factor it, but we needed a Pythagorean identity to swap this out first so that they were all the same function so that I could then factor it. That's the big takeaway. Everything after that was hopefully just a little practice and review of older things. And we got one more here. I know you'd be sad if I cut you off after only two. And similarly here, can bring that chart back in case we need it. We didn't really need it in the last problem, but I assume it was like a test or a quiz. You would have that on scrap paper next to you and you'd be looking at it the whole time. So we have a similar thing here of two different trig functions equal to 1. So if you want to try to factor this, you typically bring everything to one side. So you subtract 1, and so it's equal to 0, but we run into the same thing we had last time, that I've got a trinomial, but these are two different functions. And for me to try to factor this like a trinomial, that pattern, I need to have these be the same, either tangent squared and tangent, or secant squared and secant. And you can't just change secant, but I can change tangent squared. I can always change the squared one using a Pythagorean identity. So you either memorize it or you look it up. What's the identity that uses tangent squared? And it's 1 plus tangent squared is equal to secant squared. How convenient, right? That the other function in it is secant squared. So what is tangent squared equal to all by itself? Secant squared minus 1. Right, so I just manipulated. I'm going to take out tangent squared, and I'm going to replace it with secant squared of theta minus 1. The rest of the equation is plus secant minus 1 equals 0. So combine your like terms, use good algebra here. But similar to the last problem, I had to do a little Pythagorean substitution first. But now hopefully you're seeing that that makes things a lot nicer, because I've got a trinomial and now it's the same function here, secant and secant. So I can go right ahead, and the lead coefficient is 1 again. So I don't have to do any AC or even, thinking about any crazy combinations and the foiling part. So I'm going to jump right to, rather than rewrite it as a squared plus a, I'm just going to say, look, I think I can handle this now. If that's secant squared, that means that's secant and that's secant. And then what multiplies to -2 but adds up to +1? So that's going to be +2 and -1, right? And now we set each factor equal to 0. And we're saying setting that factor equal to 0 will give me where does secant equal -2. Setting this factor equal to 0, I'll add 1. That says where is secant equal to +1. And does this have a solution? Is this one of those like the last problem where if it goes below -1, it's got no answer? No, because this is secant. And secant is the reciprocal of cosine. So if you think about it, or if you have to write it, that this is the same thing as saying, where is cosine? The reciprocal of -2, which is -1/2. That certainly has solutions. Two solutions, in fact. Where is cosine equal to 1/2? That would be a reference angle of pi/3, or 60 degrees. But where is cosine negative? All students take calculus. And where is cosine negative? Cosine's positive in quadrant 1 and 4, so that means it's negative in 2 and 3. So reference angle of pi/3 in quadrants 2 and 3. So pi/3 in quadrant 2, 1 less than the denominator, 2 pi/3. Quadrant 3, 1 more than the denominator, 4 pi/3. In degrees, that's 180 minus 60, which is 120 degrees. 180 plus 60, 240 degrees. So there's our two solutions for that little equation. And how about secant being equal to 1? If you need to rewrite that as cosine, fine. What's the reciprocal of 1? It's still 1. Where is cosine equal to 1? I feel like we've answered this. Actually, maybe not this exact one. That would be when is the x-coordinate 1, and that's only one location, and that's right here. And based on the way the interval was specified, that would be at 0 radians or 0 degrees. Not 2 pi or 360 degrees because it was inclusive around the 0 and exclusive around the 2 pi. So there we go. Another trinomial factoring problem. That one again required that Pythagorean identity to swap that out so you could change it all over before you factor. So wanted to show you a couple of those too. Hopefully you'd be good at spotting those now. So, pretty tricky stuff here when you're putting a lot of ideas together. So easy to get confused. Kids do frequently. So hopefully this helped a little bit. But if you have questions, just ask. If I can clear anything up, I'm happy to do so. Take it easy and keep working hard.